So good morning. We have two talks before a coffee break. The first speaker is Maria Chudnovsky from Princeton Math Department, who also did her PhD at Princeton and was a Veblen instructor and a postdoc, had a postdoc from the Clay Institute before going off to Columbia and then coming back to Princeton. Was you couldn't escape, right? So it's a kind of a attractor there. She's won quite a number of awards, gave a 2014 ICM talk and a MacArthur Fellowship, which is a genius award. Today, she's going to talk on forbidden induced subgraphs, structure, and algorithms.
Hi, good morning. Thank you for the introduction and thank you for inviting me and thank you for coming to hear me. That's the hardest part. What I'm going to talk about is basically what I've been doing for the last 5 years with hopefully emphasis on the more recent things. But I think I'll spend most of my time kind of motivating things and putting things in context because, this is not a conference in graph theory. So I think it's much more interesting for you to hear why I do these things than exactly what I do. So, all right. And I should also say, so only my name is on the title slide, but all the theorems are joined with different people. And I tried to write down who did what, and I'll try to say who did what, and none of this is just my work. Okay. So I'm a graph theorist. I study graphs. Graphs have vertices and edges, and always the vertex set is denoted by V, and the edge set is denoted by E. And what I've been mostly working on in my career is understanding the structure of graphs that are the structure of graphs that are described by configurations you cannot get by deleting vertices. I'll say this more precisely in a minute, but here's a graph, and I promise you that no matter how you delete a subset of vertices, this little configuration or big configuration cannot be reached. And then I try to say, I try to either describe the structure of graphs like that or answer questions about them, but this is always or almost always, usually the setup. So let me make this more precise. So this containment relation where what you're allowed to do is to delete vertices is called taking induced subgraphs. And let me make this more precise. So H is an induced subgraph of G. If you can get H from G by, you pick a set of vertices, and these are going to be the vertices of H. And then the rule is if you pick two vertices and they're adjacent in G, they have to remain adjacent. If you had two vertices and they are not adjacent in G, then they have to remain non-adjacent. So it's sort of restricting to H, restricting to a fixed set of vertices. You commit to a set of vertices, and then that gives you the graph. So let me just do a quick example. So this is G. This is an induced subgraph of G because to get, see if I can do it with technology, because to get this from that, what you do is remove this vertex, right, and just keep the outside 5 cycle, and you get that. Now this is not an induced subgraph of G because why? Well, they have the same vertex set, but they don't have the same edge set. So I would need to remove an edge between two vertices that I committed to keeping, and that's not allowed. And a word I'll probably never use, but the family is hereditary if it's closed undertaking induced subgraphs. All right, so now we know what we're talking about. Probably one of the most well-known hereditary families closed undertaking induced subgraphs is the family of perfect graphs. So perfect graphs were defined by Claude Berge in 1961. And what they are, they're graphs that behave as well as possible with respect to color. Now, what do I mean by that? So you know what graph coloring means? You want to color the vertices so that adjacent vertices get distinct colors. And then you ask how many colors do you need? And there's an obvious lower bound, which is if you have a clique, if you have a set of pairwise adjacent vertices of size 100, all these vertices have to be colored with different colors. And so you need at least 100 colors. So for every graph, the chromatic number is at least the clique number. Perfect graphs have the property that this lower bound is achieved. and not just in the graph, but also in all its induced subgraphs. So somehow it's these graphs are colorable as efficiently as you can possibly imagine. And so Berge defined them, and he asked some questions about them. But what's amazing about this class of graphs is that even though they kind of started in, in this world of coloring, it turns out that they have all kinds of other interesting properties. So somehow that's how you know that you found a good object. It's interesting because of this, but actually it's much deeper than that. It also has this and this and that property. So I'm not going to say all of them, but I'll say some. So we already said behave well with respect to coloring. A graph is perfect if and only if its complement is perfect. Now, what's the complement of a graph? It's when you reverse all the adjacencies. If a pair was adjacent, you make it non-adjacent. If a pair was non-adjacent, you make it adjacent. Now, just from the definition with respect to to coloring, it's a complete surprise why these graphs would be closed undertaking complements. Turns out, if you look at polytopes associated with their stable sets, something very kind of nice is going on there, and that's one could say that's the reason they're closed undertaking complements. Another, and by the way, Berge conjectured that if we define perfect graphs. Another fact about perfect graphs that Berge also conjectured, and it was proved with my collaborators, is that you can list all minimal abstractions to being perfect. So in terms of induced subgraphs. So a graph is perfect if and only if it does not contain odd cycles as induced subgraphs and complements of odd cycles as induced subgraphs. So an odd cycle is this or that. Extrapolate. And the complement of an odd cycle is the complement of this or that, and you can extrapolate. And it's very easy to see that these are not perfect. So since being perfect is closed undertaking induced subgraphs, you have to exclude them, but turns out it's enough to exclude those obvious examples. So that is a strong perfect graph theorem. Now, of course, if you believe this theorem, you shouldn't be surprised that perfect graphs are closed undertaking complements because the set of abstractions is self-complementary. Okay. So then there's another thing about perfect graphs, which again relates to the property of their stable set polytopes, and that's the fact that there are various algorithmic problems that are NP-complete in general, but on perfect graphs you can solve them in polynomial time. Among those problems are finding the largest clique, finding the largest stable set. A stable set is a set of pairwise non-adjacent vertices, finding an optimal coloring. There are several more that I won't mention, and that's a theorem of this group. Now, this theorem, it seems like a theorem in graph theory, but actually it's a theorem in combinatorial optimization, because their kind of great insight was to represent the problem of finding largest clique or maximum weight clique as a semi-definite program, and then they had tools from combinatorial optimization that they could use to find an optimal solution. One of my favorite problems is to try to do this just by tools of graph theory. I always talk about this. Whenever I give a talk, I mention this problem in the hope somebody would solve it. Right? So, it's a graph theory problem, design an algorithm to solve it in terms that you can understand in terms of the graph. It turns out if you just take the optimization, like the ellipsoid method, and try to follow what it does, you can't understand it in terms of the graph. Many people have tried and they couldn't. Okay, so that's just advertisement for the field of induced subgraphs through the lens of perfect graphs. Now, I've been talking about this lovely hereditary family, and one might optimistically think that all hereditary families are nice, but that's completely false. There are lots of very ugly and unpleasant hereditary families. So one property that we liked about perfect graphs is that you could color them with few colors. In general, it's not true. There are hereditary families where you need to color graphs in order to color a graph in them. You need many more colors than its maximum clique. In particular, triangle-free graphs. They're triangle-free graphs with arbitrarily large chromatic numbers. It's not true that if you restrict to non-trivial hereditary family, you can solve problems efficiently. For example, finding max clique is NP-complete in the class of graphs with no stable set of size 3. That was a nice family. In general, families, hereditary families could be not nice at all. But there's a conjecture that's a famous conjecture in the field that tells you that there's a big difference between a family where something is excluded as an induced subgraph and a general family of graphs, or the family of all graphs. And so I'll say what it says in a minute, but somehow the point is, if you exclude an induced subgraph, it looks like something very local that you told me about the graph, right? If you exclude a graph on 10 vertices, a priori, it seems like you just have information about 10 tuples of vertices. And it's a good question whether something global has to happen if you told me something about every 10 tuple of vertices. And what this conjecture says that, yes, something global has to happen, and there are weaker versions of it that have already been proved that suggest that maybe numerically this is not right, but something global does happen. So what the conjecture says is that whatever you exclude for any graph H, if you exclude it as an induced subgraph, then suddenly you have either a surprisingly big clique or a surprisingly big stable set. Now, what's surprisingly big? Right? So in order to be surprised, you need to know what's normal. So normal is log the number of vertices. There are graphs where the biggest clique is log the number of vertices, and the biggest stable set is log the number of vertices. However, if anything is excluded as an induced subgraph, the conjecture is this number jumps to be the number of vertices to a power. And various weakenings of that are known. Okay. So that's somehow I feel like you can't give a talk about induced subgraphs without mentioning the Erdescheidel conjecture. So this is my mention of the Erdescheidel conjecture. So now moving on. So we said some hereditary families are nice, some hereditary families are not nice. So now an obvious question is, how can you tell which ones are nice? And for the rest of my talk, the meaning of nice that I'll focus on is structure and algorithms. I'm not going to talk about coloring at all. That's a different separate branch that I don't want to talk about right now. But what I want to think about is families of graphs where you can describe the structure of their members and where you can design efficient algorithms. And usually these two things are closely related. You understand the structure, you can use it to design algorithms. If there's an efficient algorithm, usually it's because something's going on structurally. Oh, so that's the topic from now on. Now, there's a tool in graph theory specifically for that structure that can be harnessed for algorithms, and that's called tree decompositions. Now, I always say this slide is for a very niche group, because if you know what the tree decomposition is, you don't need it. If you don't know what it is, you probably won't learn it from this one slide. So, but this is for people who knew and forgot. But I'll try to kind of give enough intuition so that even if you've never seen this before, you'll still understand what I'm talking about. So what's a tree decomposition of a graph? You take a big complicated graph and you try to represent it by a tree. Now, what does it mean represent? So there are 3 rules. First of all, you take a tree, and every vertex of the tree, you associate a subset of vertices of your graph. And you call that a bag. So like imagine a tree and you hang bags on its vertices, and that's all the vertices of the graph you're trying to represent. The bags don't have to be disjoint, they don't have to be connected. So far, no rules. So now, okay, so that's I represented vertices. Now I want to represent edges. And what that means is for every edge of my graph G, I want there to be a bag that contains both ends of this edge. So now all vertices are captured, all edges are captured. And now there's one more rule. And that's kind of what ties everything together. If you look at the vertex of G and you see where in the tree it appears, in which bags it appears, that has to be a connected graph. That has to be a subtree. So these are the 3 rules. Maybe let's just quickly do an example. But again, the point is you take a complicated graph and you try to record a lot of information about it via tree. And you're allowed to use whatever tree you want, right? All trees are equally simple to me. So, okay, let's do an example. So this is a graph. This is its tree decomposition. So notice that this graph is a tree, so somehow I'm probably not going to gain much. So what do I need to do? I'm using the same tree. I need to tell you what the bags are, right? So for every node of this, I intentionally use vertices for G and nodes for the tree. So for every node of this, you need to put a subset of vertices of that. And the way to do it is you designate a root. And now for every vertex, there is a unique path to this root. And so for every vertex, there's a unique neighbor and its unique path to the root. So in the node corresponding to it, put it and its unique neighbor. So I designated 3. Here's the path. 1's unique neighbor in this path is 2. So I'm going to put 1, 2 here. This is 4. His unique path to 3 is 4, 3. So I'm going to put 3, 4 here. So that's a tree decomposition. And notice that I could do it to any tree. I did it with bags of size 2. Very good. So this is another example that I would have done in a longer talk, but now I'm going to skip it. But notice that this is not a tree, and bags here have size 3, and that's significant. Okay, so now, okay, so here's a tree decomposition of any graph. Take a one vertex tree and put all the vertices of G to this the bag at this one vertex tree. That's definitely tree decomposition, but you definitely didn't gain anything. So now you want to measure how efficient your tree decomposition is, how much simplification you got by taking a tree decomposition. And classically, the way it's measured, you look at the size of the bags, right? So you take as complicated a tree as you like, but you want to make the bags as small as possible. And the tree width of a graph is with your favorite tree, how small can you make the biggest bag? And then we say G has small tree width means it's close to being a tree. Now that I think is people who invented tree decompositions also invented this phrase, but trees have tree widths, well, the tree width 1 because you say size of the biggest bag minus 1. All right, and then things that are not trees have tree widths bigger than 1. So it's really not a coincidence that here I was able to do it with bags of size 2, but here I needed bags of size 3. Okay, so very good. That's something that was used in graph theory a lot for many years now. So now, why do we like it? Well, it turns out if you have a representation of a graph, a 3D composition of a graph with small bags, you can design all kinds of algorithms using this representation. And then it's a separate fact that actually, if you have a graph with small tree widths, you can efficiently find the representation. So somehow, like often, there's a gap between existence and algorithms, but here there's no gap. If you have a graph with small tree widths, you can find the representation and then run algorithms. And the way you run algorithms is using something called dynamic programming, which I'll explain in a second. The problem I'll always talk about is maximum weight stable set, which means you have a graph, you have weights and vertices, and you want to find a set with no edges in it of maximum weight. But really, it is just a representative of many different problems. But that's the one I'm going to talk about. So let me just very quickly explain something about dynamic programming. So here is your 3D composition. And let's say I'm trying to find a maximum weight stable set. So then what you do is, first of all, in every leaf, for every subset of this leaf, find the biggest stable set that contains it in this leaf. And you can do that because all bags have bounded size, so you can look at all subsets. You can, this is all constant, so you can do it for each leaf. So now go one step up. Look here. For every stable set here, find the biggest stable set that contains it in this part of the tree. Now, what's interesting is that you know how to do it because of properties of the tree decomposition. You look at this set, you look at its intersection with this, and take the answer here. You look at its intersection with that, and take the answer here, which you've already computed. And now you take the union, and that's the answer. So, right, so now that's something you can continue, and finally you'll get the biggest stable set. For every subset here, you'll get the biggest stable set containing it in the whole graph. And that's what you want. That's called dynamic programming. Now, notice that demanding that all bags have bounded size was really an overkill for this method, because what I need to be able to do is look at all maximal stable sets here, right? If something is not a stable set, I don't need to think about it. So, and I don't need to do it in constant time, I need to do it in polynomial time if I want a polynomial time algorithm. So this allows me, bounded tree-width allows me to look at all subsets in constant time, but all I want to do is look at all maximal stable sets in polynomial time. There's a big gap there. There's probably something one can do. And so there's a new, there are several things people have been trying to do with that. So one thing you can do is don't ask for bounded tree-width, ask for tree-width which is logarithmic in the number of vertices. Well, if the tree-width is logarithmic in the number of vertices, you can still look at every subset of every bag in polynomial time. So that just works exactly the same. And that's this slide. So now what if I'm not quite so successful? What if I manage to get tree-width which is polylogarithmic in the number of vertices, right? Log the number of vertices to some power. Well, then what you're gonna get by this approach is not a polynomial time algorithm, but a quasi-polynomial time algorithm, right? Something that tries to time n to polylog n. But the thing is, it's in some sense it's still very satisfying because it's so if you think about an NP-complete problem, and then in some class of graphs you found a quasi-polynomial algorithm, then you basically know that in this class of graphs it's not NP-complete. There are various complexity equivalences there, where finding a quasi-polynomial algorithm, unless the world is not at all how we imagine it, finding a quasi-polynomial algorithm is probably the same as saying this problem is not NP-complete. So that's, given that all these algorithms are, when it's polynomial, the exponent of the polynomial is 1000. The practical aspect is not there. It's a question: is it NP-complete or is it not NP-complete? So in that sense, quasi-polynomial algorithms are almost as good. Okay, so this was just playing a little bit with the size of the bags. But now let's make it more interesting. Again, remember, all we want is to look at maximal stable sets in a bag in polynomial time. Well, if a maximal stable set in every bag has size 10, right, if there are no stable sets of size bigger than 10 in a bag, then I can look at them all in time n to the 10. That's polynomial. That's good enough. So that's a kind of newer way to measure tree-widths, or to measure the complexity of tree decompositions. Ask how big a stable set you have in a bag. Right? And if the stability number of every bag is bounded, then you can solve max weight stable set in polynomial time. If the stability number is polylog n, you can solve max stable set in quasi-polynomial time. So somehow that's a different way to measure complexity. Instead of just looking at size, you look at something structural and you ask how complicated that is. Okay. So let me just say this once again more precisely. So far we had tree width, just the size of the bags. Now we're going to think about tree independence number, which is you look at the tree decomposition, you ask how big a stable set can you find in a bag, and then you look at the tree decomposition where that is minimized. And this was introduced a few years ago by this group of people. Okay. So now let's talk about some theorems. So what we want to understand is which graphs have bounded tree widths, or maybe bounded tree independence number, or maybe something else like that, maybe logarithmic tree widths, and somehow to do it in the world of induced subgraphs. The answer to this question is known if instead of induced subgraph you think about graph minors. That's a theorem of Robertson and Seymour from the 1990s, a very famous theorem, but induced subgraphs are very different from minors. Minor is something very global, and induced subgraphs is something very local. So what my collaborators and I have been trying to do for the last several years is try to understand what you can say about tree width and other tree decomposition parameters in the realm of induced subgraphs. Right? So ideally find abstractions to, the most basic question is find the set of induced subgraph abstractions to bounded tree widths. So let me talk about that a little bit. So if you want to find a set of abstractions to something, the first thing you need to do is list some things that have this parameter big, right? That's where the abstraction is going to come from. If you want everything with tree widths at most 100, you better have some examples of things with tree widths at least 101. So luckily, people have been thinking about tree widths for a long time. So there are many families of graphs with large tree widths that are known. Among them are complete graphs, complete biped graphs, Now this makes sense, right? This is a very dense graph, so they're far from being trees, so you expect that they have large trivets. But this is a very sparse graph that still has large trivets. So what is it? It's called, what's drawn here, it's called the wall. It's a cubic planar graph. And then you can subdivide the edges. And then that makes it more and more sparse, but the trivet is still big. Okay, so that's some examples. And actually, it turns out in the world of minors, that's enough. If you exclude this as a minor, then your trivet is bounded. But like I said, in the world of induced subgraphs, it's different. And the very first thing one notices is that if I take this and I change every junction from being a claw, like a tripod, to being a triangle, that gives me another graph with large trivets. I'm not going to explain it, but it's true. And there's a way to say it. This graph is the line graph of that graph. So that's another thing you need to exclude if you want to exclude something as induced subgraphs and get bounded trivets. And you can notice that none of this is an induced subgraph of that, and none of this is an induced subgraph of that, because this has vertices with 3 pairwise non-adjacent neighbors and no triangles, and this has triangles and no vertices with 3 pairwise non-adjacent neighbors. It's really no chance. Okay, so that's kind of the inheritance we got from graph minors, that you have to exclude those. Now, just one thing to mention, if I fast forward several years and instead of bounded trivets, I want to think about bounded tree independence number, then it's all the same, except the very first one. A big clique, a big complete graph, has tree independence number 1, but has trivets huge. So. Okay, so moving on. Okay, so now you don't need to read what it says. I'll say it in words. So like I said, this is what came from graph minors, and very briefly, people hoped that maybe this is it. If you exclude those things, as induced subgraphs, you would get bounded trivets, but it's false. And it's false kind of in a very serious way. Something much, much weaker is false. So Cynthia and Trotnion in 2019 came up with an example with a family of graphs that don't contain cliques of size 4 and don't contain induced cycles of even length. Now, if you don't contain an induced cycle of even length, in particular, you don't contain this, which you can redraw as that. And notice that this is K22. So you forbid a complete backtrack graph, a very small one. Now, it's also not very hard to see that this contains induced cycles of the even lengths, and this contains induced cycles of even lengths, just because, for example, this guy contains something called the theta, 2 vertices, and 3 pairwise disjoint paths, 3 pairwise disjoint paths between them with no edges between the paths. And then, so you look at this, and 2 of the paths have the same parity, and this is an even cycle, induced even cycle. And the other one is something similar. So, right, so the family that Cynthia and Trotnion constructed don't have any of the abstractions we listed. In fact, don't even have tiny little fragments of these abstractions. And yet, in this family, their graphs are arbitrarily large trivets. So this was completely false, unfortunately, just to hope that these are all the abstractions. And then they tried to fix the world and throw in other assumptions so that those basic abstractions would suffice. For example, they conjecture that if you bound the degree of the host graph and you forbid this basic abstractions, then the trivet is bounded. That's true. That was proved by Korhonen. And I'll try to later say a couple of other things, a couple of other fixes that they proposed, which were all true. So they really kind of understood how it works. You know, the whole thing is false, but any of the following will fix it. So I hope I'll get to it. All right. Let me maybe skip this because it's not so important. But okay, so we have the basic abstractions. If you bound the degree of the host graph, forbidding the basic abstractions as induced subgraphs guarantees bounded trivets. But what if the degree is not bounded? So then the question becomes, exclude all the basic abstractions, and that's those. And I'm going to have a parameter t here, right? Like I want to tell you if I'm excluding K3 or K100. I expect different bounds on the trivids depending on how big a basic abstraction I exclude. So I'm going to call them T basic. And then the question becomes what else? Right? And I'll say a graph is T clean if it doesn't contain any T basic abstraction. So the people started thinking about it, and there are various other examples. I'll say something about this one mostly because it has a cool name. This is called the Death Star. Right? If you reflect it, you'll see why. You take a path and you take a vertex and give it a neighbor, and then this makes 2 intervals. You take another vertex, you give it a neighbor in each of the interval. This makes 4 intervals. Take another vertex, give it a neighbor in each interval. This makes 8 intervals. You can probably understand how this continues. So anyway, this is just some other examples which are nothing like the basic abstractions. Okay, so now there was a little more examples, a little more bad examples. So then we said, okay, well, now maybe we can try and prove some positive theorems, say if you forbid this and this and that, you do get bounded trivids. And the first thing we tried was forbid the basic abstractions and one more graph. So for which graphs is it true that if you forbid the basic abstractions and this graph H, the trivids is bounded, and I want it to be if and only if. And it turns out that has a nice answer. It's graphs that look like this. So it's a graph, each of whose components is a subdivided star. And it's not very hard to see that it has to look like that because of this example. If you take this example, and now you can take each red vertex and give it some more neighbors, but just like make sure the neighbors are not tangled up. Everybody has its own area where its neighbors are. And then in order to exclude some, in order to not get that example, which has large trivids, you have to exclude something that's disjoint union of stars. And it turns out that's enough. Okay, so that was 3 years ago. So then we said, well, okay, we did one graph. Now let's do a finite family of graphs, basic abstractions plus a finite family. And there is an answer. I'm not going to say it because it's hard to say, but somehow it turns out it's the same answer. It's whatever finite families will disallow this, that's the finite families excluding which guarantees bounded trivids. So that's what this theorem is. Okay, so then we became optimistic. We said, okay, well now it's time to get the whole thing, but we can't do that, hopefully yet. But there are 2 things that we can do. So first of all, it's this theorem, which is sort of nice. What it says is, if I have a graph with huge trivids, then it has 2 completely unrelated bits of pretty large trivids. And it's a phenomenon that it happens in various other when you study various other parameters, most notably graph coloring. There's something called the Erdős-Sahar conjecture that says if you have a graph with huge chromatic number, there are 2 far apart subgraphs with pretty large chromatic number. So, but this is the same for trivids. If you have a graph with huge trivids, then it has 2 big subgraphs, big induced subgraphs of pretty large trivids, and there are no edges between these 2 subgraphs. Except I'm lying a little bit because, for example, it's certainly not true for a big complete graph. Right? It doesn't have anything anti-complete to anything, and it's not true for a big complete biptide graph, and it's also not true for the Death Star. But if you're not this or this or that, then it's true. If you don't contain this or this or that, then it's true. And then the first theorem basically says if there's a certain structure that you contain, then we understand all the abstractions. So now we can, instead of, now we can exclude something much more significant than we used to. Okay, so let me not say. So now remember I told you I would come back to what Trottignon and Cintieri and Trottignon said to, trying to fix the basic abstractions, trying to fix the problem that they created, where they showed the world doesn't work well. And their example was a subclass of graphs with no induced cycle of even lengths. So then they tried to see what additional conditions you can impose on graphs with no induced cycle of even lengths to guarantee that they have bounded periods. And that's somehow natural in graph theory because it's a graph class that people think about a lot. Many people agree. I should never say everybody agrees, but many people agree that it's an interesting class to study. So one thing they said is if you exclude this graph, which is called the diamond, then the periods becomes bounded, and it's true. Another thing they said is that if you exclude a large complete graph, then the periods is not bounded, but this is logarithmic in the number of vertices. And we already said the logarithmic periods is almost as good as bounded periods for most purposes you can think of. And that's also true. So somehow there are two ways in which they were able to fix the world. Once by adding a condition, and once by asking for a slightly weaker, but morally very similar conclusion. And let me skip that. But what I do want to say is that, okay, so there was periods, and then there was tree independence number. And it's kind of interesting to understand, like if I have a class with where I exclude a big clique and there's bounded tree widths, is it true that if I now allow big cliques, then there's bounded tree independence number, right? Because somehow the way we think of it, the main difference between tree width and tree independence number is a large clique is good for you or bad for you. So there was a conjecture that it's true in general every time excluding a big clique causes bounded tree widths. Tree alpha is bounded, tree independence number is bounded, but that's false. That was disproved. But sometimes it's still true, and we don't understand why in some nice natural cases it's still true. But the one case I want to mention is this case. So back to the even whole-free graphs, right? We just said that if you forbid a big clique, tree independence tree width is logarithmic. But if you don't forbid a big clique, tree independence number is polylogarithmic. Right? It's this theorem. For every even whole-free graph, tree independence number is polylogarithmic. And I already said it, but I'll say it again because it's important. As a corollary, you can now solve a big set of natural problems in quasi-polynomial time on even whole-free graphs, which was a big open problem in the field. Again, I listed some. There are many more. And let me stop here. Thank you.